So please begin.
Okay. Welcome to everyone. Thank you for joining us for today's webinar. My name is Gaurav Pandania, lecturer from Mechanical Engineering Department from PIT Studies. Now, Parul University is the leading provider of innovative graduates. Now, today we are presenting a webinar titled as Applications and the Importance of the CFD in Mechanical Engineering. It will be presented by Mr. Anand Darji, sir. He is a CEO of Pi Consultancy Services. Sir has a huge experience related to design field. If you have any questions during the presentation, please type my number 997423964. I will bring up during the presentation. We will also have time for question at the end. Now, without waste of the time, I invite Anand sir with great knowledge and expertise on the subject. Please, sir, Anand sir.
Thank you so much, sir. And thank you so much to Parul University for providing me this opportunity to present a talk on the applications and importance of CFD. Sir, am I audible properly?
Sure, sir. You are audible.
Okay, great. Thank you. So today I'll be discussing about the scope and opportunity lie in the field of computational fluid dynamics for the mechanical engineering. Okay, as such, talk about the CFD at the pre-engineering level, that is for the diploma students, is a kind of a new concept, and that's what our Pi Consultancy Services is also aiming for. We are aiming to create an awareness about the computational fluid dynamics in the field of mechanical engineering and automobile engineering, along with the aerospace and biomedical engineering. So at the pre-engineering level, so at such till the diploma level, students are more aware about the CAD modeling softwares and all. But I would like to brief about why we should also enter into the new era that is called as the analysis dimension. And this is the new dimensions that we are providing to the industry using the platform of computational fluid dynamics, because as we all aware about the field of mechanical engineering, where we are more involved with the design of the components and then after manufacturing of the components. But in between the design and manufacturing, we know that there is an important aspect called as the testing. Okay, so when you go for the testing, whether it is your destructive or non-destructive type of testing, okay, this testing is always kind of a cost adding method. Okay, and if it gets failure, you need to go back and go for the new design concept. So what we are trying to introduce here is we are providing a platform to the industries, to manufacturing industries and the design industries. Okay, and we are providing the analysis-based softwares. So we all know that the science and engineering, which the domain in which we all are. Okay, this domain is mainly based on the theory concept, the modeling concept, and the experimental concept. Okay, so if you look at the era of the evolution of the engineering field, or say the evolution of the science field, okay, very first thing happened was about theory. Okay, so we have seen that there were a lot of new theories and evolutions were happened in the domain of science and maths during the 1600 to 1900. Okay, and a lot of theories that we are studying right now, whether it is Archimedes principle or Newton's law of motion, okay, or Einstein's theory of relativity. Okay, all these different theories were evolved during those era. Okay, then the era came to implement this theory. So the people have started building the experimental setups. Okay, so they created laboratories and they have started working on it. Okay, so if you look at the Large Hadron Collider experimental method that is currently taking place, okay, where they are trying to find the God particle. Okay, so that finding the God particle, this concept was very it came very early stage. Okay, but now people are performing experiments. Okay, in the similar fashion, we as a student at a diploma level or at a mechanical level, you are having different laboratory experiments. Okay, for example, if you look at your fluid mechanics syllabus, okay, you'll be having experiments regarding the Reynolds experiment. Okay, now Reynolds did his experiment long back. Okay, and based on that, he gave a theory. Okay, that if the Reynolds number, which is the non-dimensional number, will fall into this and this criteria, it will become a laminar flow or transition flow or turbulent flow. But still, in order to understand it in practical manner, we are having this in the laboratory session, right? Now the era came about the modeling. Okay, so the thing is, we have done experimentations. Okay, but sometimes the experimentations are too costly to handle, right? So we all know that for experimentation, we need to have the experimental setup. Okay, for that, we need to create an environment. If that environment is not available, if it is absent, then how to do that, this type of experiment? So people have started working on the third dimension, that is called as the modeling. Okay, so people have started working on the modeling, that is the CAD modeling, and then they are simulating the entire experimental work into computer-based work. Okay, so that is what we call as the simulation, right? So this is the era of simulation, okay, where rather than taking a lab-based experiments, which is a too costly, we are providing a substitute called as the simulation analysis, right? So the question is, why CFD? Okay, there are different types of analysis. There are different types of, the non-destructive testing methods. Okay, but why is CFD, right? So if you look at CFD, okay, it comes from two different dimensions. One is the modeling and simulation, and second is the computational fluid dynamics. Very first thing is you need to model the entire problem, okay, and then you need to take it to the CFD, or that is the computer-based analysis. Okay, so from the Einstein's very famous quotation that theory is something that nobody believes, okay, except the person who made it, right? And experiment is something that everybody believes except the person who made it, right? So looking at this concept of experimentation, okay, people are now trying to simulate the entire environment into a computer-based model, okay, and then they are performing different analysis, right? So till now, people know that in CFD we are having one computer, and that computer gives you different data in terms of some colorful diagrams. Okay, so in this presentation or in my today's talk, what my message is that this CFD is not just about the colorful fluid dynamics. Okay, you will learn a lot in terms of mathematics and the physics that we have studied in the engineering, in the very beginning of the engineering. Okay, so we are trying to bridge this gap between what generally people have perception about the CFD, right? So people have till now perception about CFD like they are having a computer, okay, and computer gives you are doing something, and computer will give you some sort of colorful diagrams. These colorful diagrams will be having some sense, and that will be presented, right? But whether this data which you are presenting in terms of colorful diagrams, okay, this data are really sensible, are this data are realistic data, how will you come to know? Okay, there are a lot of things that I will be discussing that gives you an in-depth idea that these colorful diagrams are not those type of interesting phenomena for a lot of conceptual CFD people. Okay, they know that where and how one can trigger and they can get this type of diagram. Okay, so the thing is, you should know some fundamental about the computational fluid dynamics and its relevant branches or relevant subjects. Okay, so this type of diagrams are being simulated by a CFD engineer, okay, using his knowledge. Okay, and so the CFD is the analysis of systems that involves fluid flow, heat transfer, associated phenomena such as chemical reactions by means of computer-based simulation. Okay, so I will be discussing about many different, the concept that one can implement using the CFD analysis. Okay, but for that you should have some fundamental knowledge about your fluid mechanics, heat transfer, solid mechanics, aerodynamics. Okay, so for example, if I take an example of structural analysis, okay, so in the case of structural analysis, we should know some sort of material property. Okay, so we have an entire subject called as material science in mechanical engineering. Okay, along with that, we should have some fundamental knowledge about the solid mechanics, or say mechanics of solid, which you either call as MOS or SOM. Okay, so that material, that subject knowledge is also very important, because where to apply load, okay, how the fracture will occur or how the deformation will take place. Okay, it depends on our fundamental knowledge only. Okay, so if you are from the domain of mechanical and aeronautical, okay, we are learning subjects like heat transfer, fluid mechanics, aerodynamics. Okay, so when you do external analysis or internal analysis, some sort of aerodynamics analysis or some sort of knowledge of the aerodynamics is also an important dimension. Okay, so the CFD is one of the important parameter, okay, where you don't need large experimental setups. You don't need to put a lot of cost. Okay, so it is a cost cutting method. Also, you don't need to simulate an environment so that your time is also not consuming here. Okay, so you have a computer, so it's a cost cutting. You have you do not have to create an entire environment for that, so it is also a time cutting. Okay, it is also like in the absence of analytical solutions. Okay, so sometimes you are performing entire numerical calculation. Okay, but there are many problems, realistic problems, which we cannot solve using our hand calculation, which is an analytical calculation. And for that purpose, we need to simulate, we need to switch to another platform where we can do it in better manner. Okay, so the CFD is there. Okay, also it is helpful in the non-measuring problems. Okay, so those problems which you cannot measure, okay, that can be simulated here. Okay, and a lot of unsolved problems can be solved easily. Okay, so that is why the CFD is one of the most advanced and evolving field in mechanical and the aeronautical field. So we have seen that there are three methods like experimentation, analytical, and the numerical. Experimentation methods are most realistic because it gives you the real life environment. Okay, you are entirely performing that experiment in the real life environment using the required atmosphere. Okay, but there are certain disadvantages. Okay, like the equipment is required, scaling problem is there, measuring difficulties. Okay, probe errors. Okay, and also the cost associated is also very high. In the case of analytical, which is the hand calculation, okay, it is a formula based calculation. Okay, it requires a restricted simple geometry. Okay, so you cannot have analytical solution for the complex problems, complex geometries. Okay, you can have analytical problems for the simple problem, simple geometries, like so like Poisson flow, okay, Coulter flow, this type of flow which is between two surfaces. Okay, they have analytical solutions. Okay, but you will see when you solve this type of problems, okay, using your hand calculation, you will find that it requires a large time. Okay, and also there are a lot of things that we need to take care during the analytical calculation. Okay, a single mistake in the hand calculation will lead to a garbage. Okay, it will give you a wrong result. So a very extreme care need to be taken during the analytical calculation. Whereas if you have the numerical do have disadvantages, like there are some truncation and round off errors. Okay, because in order to look at our entire, if you do not have supercomputer and you have limited computational resources, what we need to do is we need to assume some parameter, because we cannot run our entire simulation for long hours and long days, right? So we are taking up some rounding errors. Okay, so that rounding errors is there, which is not providing the accurate result. Okay, and sometimes the boundary conditions. Okay, so these boundary conditions also one need to take care. Now there are a lot of applications of CFD. If you look at here, okay, application of CFD is there in the field of aerospace, in the field of sports and aerodynamics or building aerodynamics, then chemical engineering, biomedical engineering, electronics, environmental aspects, HVAC, that is heat, ventilation, and air conditioning, and the process industries. Okay. Apart from this, the automobile and the engine divisions are also using CFD at a large scale. Right. So first of all, if I discuss about the applications, so here is the aerospace applications. You can see simulating the aircraft. Okay, the flow over an aircraft or its wing. Okay, its radar. Okay, its vertical fins. This all can be analyzed using the CFD. Apart from this, the flow through a gas turbine engine can be analyzed. You can see here, this is the gas turbine. Okay, and in the gas turbine, the flow is entering. Okay, then you are having a large fan. Then you have the compressor. Then you have combustion chamber. Then you have turbine. Then at the exit, you are having nozzle. So you are entirely simulating the flow behavior through this gas turbine engine. Apart from this, rocket and missile, we have different noses of rocket and missile, and we analyze that how the shock will propagate over the nose structure. Okay, this problem is more complex when we have the re-entry vehicles. Okay, so we all know that when the capsule enters, that means when the astronauts return from their journey, okay, back to Earth. Okay, so they are seated inside somewhere in this type of capsule. Okay, so this is what the location of those astronauts. Okay, and this is the capsule. Now this capsule is entering into the Earth surface. Okay, all of from your space to enter into the Earth surface. And what happens? There is a large friction that takes place, and so a specialized design of this capsule is required in order to detach the shock that is occurring at its tip. So that's why we have this type of blunt shape of the re-entry vehicles. Okay, and also the hit that occurs at the tip is very high. Okay, so when you have this type of structure, okay, the hit will be dissipated. So that's why this type of CFD will give you a realistic idea that how we can do this. Okay, now you cannot go to the space, and you cannot go with the capsule and make number of probes over there and then re-entering that capsule into the Earth surface. Okay, if you will try to do your probes will burn. Okay, so we can do this type of analysis using the computational resources like CFD. Okay, then the flow in the quadcopters. Okay, and the simple problems like flow over and airfoil. Now airfoil is having a number of applications. One of the applications that we have seen is on the design of your aircraft wing. Okay, apart from this, there are a lot of vortex generators are being used. Okay, your blade design, your compressor blade, turbine blade. Okay, these all are having some sort of airfoils. So we can do this type of analysis. If you look at the mechanical or automobile section, okay, we have the concept of IC engine. Okay, we have learned about IC engine in detail about in our syllabus. Okay, and we all know that there is some sort of combustion is happening. Okay, whether it is your petrol engine or it's a diesel engine. Okay, so combustion is taking place. Okay, when your piston is moving and there is some sort of space available. Okay, so in this region, when the combustion, the if I take an example of petrol engine, okay, you have air, okay, and you have fuel, that is your petrol. Okay, now when at the end of your compression stroke, okay, what happens? Your air fuel mixture, okay, will be having a good amount of compression happen. It's already a high pressure fuel, okay, mixture of high pressure fuel. And now when you are providing the spark, okay, that ignition is required to have the combustion. Now CFD helps you that how this combustion is taking place, because we know that in today's era or in today's world, the most common problem is the NOx emission that is happening at the exit, okay, from your silencer. So the issue is how to minimize this NOx, and this comes from an idea that the improper combustion is a responsible factor for this type of NOx emissions. Okay, so reducing this NOx is an important part, and that's why for that we need to analyze that how the combustion is taking place. Okay, so we know the concept of lean mixture. Okay, and so using the combustion in this zone, we are performing CFD analysis for that. Apart from this, there are concepts like vehicle aerodynamics. Okay, so you have different designs of cars. Okay, and you know that more aerodynamic car can give you less drag. Okay, and with that you can achieve maximum speed. Okay, so the aerodynamics helps you, the CFD helps you to understand that how the flow physics will be. Okay, so if you look at here, this is your truck. Okay, and when the flow passes over the truck, you can see there is a downstream region. Okay, and in this downstream region, a lot of turbulence is creating. Okay, if somebody is driving in this region, definitely he will be under the effect of turbulence. Okay, and we all have faced this type of phenomena. Okay, so this type of work can be done using the computational fluid dynamics. And here, the role of mechanical engineers, because mechanical engineers are the engineers who have designed these structures. Okay, they have designed these bodies, right? So when they learn one more additional tool, that is CFD tool, okay, they will be adding up some value, okay, to the society. And that's why I I prefer to learn CFD. Okay, and I suggest everybody to learn at least CFD tool along with your CAD modeling tool. Okay, so that you can enhance your skill in the industry. After nowadays the concept of bullet train. So if I give you an example, I'm also pursuing PhD from NIT Surat, and my work is at IIT Kharagpur. So my guide is responsible for taking up a railway project. Okay, so they have a large tunnel, wind tunnel. They have designed a large wind tunnel over there, and they are testing the bullet train project. They are having this project of bullet train, and they are testing the different scale models of the bullet train into the wind tunnel. Now, the cost associated to run the tunnel is very high. Okay, at the single moment when we are operating that tunnel for a single scaled model analysis, okay, we need to take a special permission from the director of IIT Kharagpur. Okay, and when they are allowing us, okay, that too at the end of your weekdays. Okay, that means on the weekend when entire institute is off, you have to take that experimentation, because the power consumed during the wind tunnel running is more than at least 3 different departments. Okay, so this is the amount of cost associated with the experimentation. Okay, along with the design of that entire wind tunnel, that is also a challenging part. Okay. So what we do is we are also doing this type of CFD problems over there. Okay, and we are presenting the results. Okay, and then when they do that experimentation, we are validating the results, right? Along with this, if you have car, okay, and you have air conditioning system inside your car, okay, you can actually simulate that how the distribution of cooling will be inside the car. So that can also be done using the CFD. So you can see there are a large number of applications of CFD in the field of automobile and mechanical engineering. Okay. Apart from this HVAC industry, which is also part of mechanical engineering, we are learning subject called as air conditioning engineering. Okay, this HVAC, which is heat ventilation and air conditioning. Okay, that is, for example, if I take the first example, this is the example which I have taken from the cooling, or say the entire air conditioning system of one building. Okay, so this is the building of some mall. Okay, and you can see you are having large duct systems. So there is a duct system you can see here. So these are the ducts. Okay, and this type of ducts you have observed. Okay, in the parking lot, in the parking region of the malls and theaters. Okay, so these ducts are opening into certain chambers or at certain floors. Okay, and these are providing you the cooling in the entire air condition in the entire malls and theaters. So that's how these entire malls and theaters are centralized air conditioner. Okay, so you can entirely simulate this type of flow physics. Okay, apart from this, if you look at your home, okay, this is the home comfort. Okay, you are having your air condition. Okay, and then you can analyze that how the distribution of air will be inside the home. Okay, nowadays people are also using this type of air conditioning in the building designs. Okay, so based on the cooling air or breeze, okay, they are creating windows and doors into the particular direction, so that the natural air or natural ventilation will help them to have to reduce the air conditioning loads. Okay. So apart from this, the process industries are also using CFD. So here is a stirrer, okay, and some fluid is there, okay, and they are stirring it, okay, and they have modeled the turbulence kinetic energy, right? Then there are environmental aspects. Okay, you can see here, these are the problems. Okay, this is the problem that one was solved at the NIT Surat. Okay, it was the thermal effluent problem from the Kafrapa nuclear power project. Okay, and in this particular project, what we had done is we had simulate that how the thermal effluents that is coming out from the chimney, okay, will be distributed in the nearby region. So based on that, we have to design the chimney height. So that was the project solved, right? Apart from this, the sports and building aerodynamics. Okay, so if students are available and if they have seen the Olympic Games, okay, they might have seen that the cyclists are always traveling one after another. Okay, they are in a linear position. Okay, they are not distributed. They are not scattered. Why? Because the first cyclist will observe the maximum drag, and rest of the cyclists will observe the minimum drag, and they are those downstream position cyclists are taking the advantage of this, okay, so that their effort to paddle the cycle will be less, okay, and that's how they are taking the advantage during this uh, uh, cyclist phenomena. Apart from this, the swimmers, okay, you have seen there is a very popular video available on the YouTube that is about the uh, costume design of swimmers, okay, and they have done CFD analysis of the Michael Phelps, okay. You know that in the Beijing Olympics he was the hero, okay, and he is still a hero for USA because he's the person uh, who has achieved I think around 8 gold medals in a single Olympics in the swimming, okay. So then after the scientists from one of the university in USA, they did entire CFD analysis of Michael Phelps, and then they come to know that how the Phelps was having additional advantage during the swimming, and that's how he was able to get 8 gold medals in the single Olympic games. Okay. Then this is the building aerodynamics. You can see this is the building aerodynamics done by Professor Bert Loken from TU Delft. Okay. Sorry, TU Eindhoven. That is Technical University Eindhoven at the Netherlands. Okay. And he has done this type of sports and building aerodynamics. He's pioneer in this field. Okay. And you can see there is a sports complex available, and there are some buildings available nearby to it. Okay. And this is the direction of wind, okay, and he is simulating this entire sports building, that how the flow will be circulated through this sports building when they will be having this type of wind load, right? Apart from this, if you have high-rise buildings just like this, okay, and this is the direction of flow, you can analyze that how the flow distribution will be, okay, so that the nearby buildings, any building which is near to it, okay, they will observe the maximum turbulence, and no building should be placed in that region. Otherwise, those building structure will fail very early. Okay, so these are the different analysis that can help you. Okay, so let me just give you one close view about. I don't know, sir, why I'm not able to. Okay, so I think due to some, yeah. So this is flow over golf ball. So you know that golf ball is having dimples on it, okay, whereas the simple ball do not have any dimples. So when you have this type of dimples on the golf ball, the turbulence will help additional, and that's why the golf ball can travel more. Okay, it can cover more distance as compared to a simple ball. Okay, so this additional advantage of turbulence is helpful. Apart from this, there is one more dam flow analysis is done. Okay, so you can see when the dam gates are open, okay, how the flow of water will be, okay, so that one can simulate this entire environment using CFD, right? Apart from this, CFD has its additional advantage in the field of biomedical. Okay, nowadays people are doing a lot. Okay, even we have solved one of the project of the biomedical. Okay, but you can see this is the blood pumping through heart. Okay, in the heart, you know that how the blood is. Okay, now blood is the thicker fluid. Okay, now the density of this fluid is different. So when you do CFD analysis of this type of fluid, okay, you need to additionally provide the data of the material or of the blood, okay, and then that is how you can do it. So if you are doing the air breathing analysis just like this, okay, you can easily see that how the fluid will pass or how the air will pass through. And this is the lungs, okay, this is the bronchi. So you can see if you are having some mass flow rate of the air, okay, through this region, how that flow rate will be distributed. Okay, so that can be analyzed using this type of biomedical analysis using the CFD. Okay, so now CFD involves three major parameters. One is the pre-processing, then the calculation, and the post-processing. In the pre-processing, what we do is we are having different tools, just like you are having your CAD modeling. So CAD modeling is also a part of pre-processing, because if you want to simulate something, for example, I want to simulate flow through a pipe. Okay, now my problem is I'm doing this project for so and so industry, which is pipe manufacturing industry. In that industry want to know that what should be the optimum thickness of my pipe, so that the hot fluid which is going to pass through this, okay, they require to have minimum kind of insulation around it, right? So that is our problem statement that was given to us. Okay, so what we need to do first is we need to analyze a particular pipe model. So we have modeled it, okay, and we have taken number of different thickness pipe models, okay, so that we can identify the optimum one. And using the geometry generation in your simple softwares, okay, whatever CAD software you are using, that can be used for the geometry generation. Then the most important thing is the mesh generation. Okay, meshing is one of the most important thing. That is what we are doing. We are discretizing the entire the three-dimensional model into number of subdomains. Okay, and then as I mentioned that our governing equations, okay, of the computational fluid dynamics that we have learned, okay, so that governing equations will be solved on each and every control volume, right? And then they will give you some sort of result, and that's how at the end of it you will achieve. Okay, it is a marching of entire governing equation from one control volume to the last control volume, and then you will get some result. Okay, you have to analyze, you have to cross verify it. Okay, and that's how we are doing it. So the meshing is one of the most important part. Second thing is the calculation. Once you have done the meshing, okay, you will be having different solver. For example, Fluent is one of such solver. Okay, so there are a number of other solvers like Convergence is there, CFX is there, okay, MATLAB is there, okay, C language is also solver. Okay, so when we do it, okay, what we need to do is we have to define some sort of boundary conditions. Okay, so we are defining some sort of boundary conditions. Okay, and based on the boundary conditions, it will calculate. Okay, it will solve your U, V, and W momentum equation, which has a Navier-Stokes equation. Okay, and then you will get some property. Okay, and if you are getting this property, and if those properties are meeting, then the simulation is called as the converge. And if it is not happening, further you need to change the inlet conditions or boundary conditions, and you need to solve it again. So that's how the Fluent works, right? And then at the end, if the solution is converged, then you can go with the post-processing. And in the post-processing, we are getting different data, right? And we are plotting different data based on the required client's requirement, okay? And we are analyzing it, okay? So these are the different set of governing equations, okay? If we look at this particular governing equation, this contains your continuity equation, X, Y, and Z momentum equations, okay? Apart from this, you have one more equation called as the energy equation. But if your temperature is not involved, the energy equation can be taken out, right? And you see in these three momentum equations, okay, you have one non-dimensional term, that is 1 upon RE. RE is your Reynolds number. So based on your Reynolds number, you can solve this non-dimensional form, right? And there are certain, as I mentioned, that there are certain, the limitation of CFD also, okay? So one of such limitation comes when you have the number of dependent variables and number of equations are not matching, right? So the thing comes that in this particular equation, okay, we have rho, U, V, W, and P. P is your pressure, right? Rho is your density. U, V, and W are your velocities, right? Now the number of equations are only 4, right? You have one mass conservation, okay, that is the continuity equation, and 3 momentum equations. We have not taken here the energy equation because it is not required. Temperature is not involved, right? So we know that we cannot solve this kind of equation, right? So what to do? So for that purpose, we also need to have additional terms, okay? And so this complexity of solving CFD is more, okay? This complexity further increases when you have the unsteady analysis, where the properties are changing with respect to time, right? So there are different methods of solving unsteady analysis, like explicit time marching and implicit time marching. I will not fall further in this domain because this is very preliminary lecture to all. So this is just an overview that yes, when you do CFD, you need to take care about all these fundamentals. You cannot simply start with the CFD. or whenever you are starting with the CFD, you have to learn this parallelly. Okay, so at least this fundamental knowledge is also required. Okay, and when you have this compressible fluid, okay, you see it is more easy to solve as compared to incompressible, right? Because in the compressible fluid, what happens? The number of dependent and number of equations are somehow similar, right? And there is no additional requirement of the pressure and velocity coupling. So those are the things. Okay, and these are different methodology that we are adopting during the CFD. Okay, and you can do you can make a comparison that when we do CFD, that is where the fluid is involved, and when we do structure analysis, where the structure failure is involved. So the CFD is mainly on the finite volume method, whereas structure analysis is finite element method. Okay, and we can do both. Okay, so in the case of structure analysis, stress analysis is generally checked for the safe working of the design. Mainly the performance of the system depends on the stress level. So we are providing some sort of boundary conditions, like where the fixtures are provided, okay, and where the loads are applied. Based on that, we are analyzing how the failure will take place, or how much load you can that particular structure can resist up to. Okay, so this type of analysis can be done in the structure analysis. In the CFD, we can do fluid structure interaction problem as well, where the structural loads can be imposed with the CFD load, that means the fluid load, and then we can analyze the entire problem. So then the problem is more complex. Okay, further when we add the turbulence, okay, turbulence itself is a big task, right? So the famous scientist Werner Heisenberg said that when I meet to God, I'm going to ask him two questions: why relativity and why turbulence? I really believe he will have answer for the first one. So Werner Heisenberg is very pioneer scientist in the field of turbulence modeling in CFD. Okay, and he has claimed that still the turbulence is something that nobody have understood, and it is very true. Okay, even when you do experimentation, you cannot observe turbulence very clearly. Okay, because to observe turbulence, you need to have the flow visualization method, and each and every flow visualization method is having their own limitation, right? But when we do CFD, okay, we are having different turbulence model, from single equation model to two equation model, three equation model, four equation model, and then large eddy simulations and DNS and etc. But the thing is, how well we have understood. So nobody have this answer, right? Along with this, famous Nobel Prize winner in the physics, that is Richard Feynman, said that turbulence is the most important unsolved problem of classical physics, right? So based on this, we can understand that turbulence is very chaotic in nature. Okay, it is so chaotic that one cannot observe with his naked eye, right? So there are a number of things added here in order to observe that chaotic nature. There are eddies, there are swirls, there are flow instabilities. Okay, so you can see the velocity. When you say that this is the velocity of the fluid, it is not actually the velocity. It is the velocity which you have taken as an instantaneous point of view. Okay, so that velocity is having mean as well as fluctuated components. Okay, and then in the case of turbulence modeling, we are taking the average out of the Navier-Stokes equation. So when we do the averaging Reynolds average Navier-Stokes equation, which is the RANS, okay, Reynolds average Navier-Stokes equation, which is the average, say, average of the Navier-Stokes equation. Okay, then there are certain number of the unknown terms left with, and these unknown terms we need to close using the turbulence model. So these are the different turbulence model available in the different solvers. Okay, and as and when you progress from one equation model towards the direct numerical simulation, that is the DNS model, okay, the cost keep on increases, right? So let me show you one video. Okay, and here in this video it is about the turbulence intensity that one can understand. Okay, so this is solved using the LES, large eddy simulation. This is the flow over an airfoil. Okay, there is small surface generated. Okay, and from there the fluid behavior is observed. You can see these are the different eddies one can easily see using large eddy simulation. Still, people are saying that the turbulence is something that is not perfectly known. Okay, so when when the flow passes over this, you can see from somewhere there, the flow separation is taking place. And that's why you are having blue region. Okay, the dark blue region is the wake zone where you are having a low momentum fluid where no velocity is involved. Okay, and further downstream to it, you can see these are the vortices that is forming the mixing, and that's why these are called as the mixing layers. Okay, and further, if you observe very neatly and kindly, you can see these are the periodic vortices. Okay, and these periodic vortices are also called as von Karman vortices. Okay, and these are the vortices that you are observing. Okay, from the bottom surface, which is the pressure side, top surface is the suction side. Okay, so pressure side is the side where the pressure is higher, suction side is having lower pressure, and this adverse pressure is also one of the important parameter for the lift of the body. Okay, so you can see the carbon vortices nicely presented here. So if you want to do this type of simulation, okay, you need to have very high configuration PC. You need to have a supercomputer. Okay, and you can do this type of fine eddy detection. Okay, using LES turbulence model. Okay, so the thing is, in India we have large scope, or we have an opportunity to work in this domain of computational fluid dynamics. Okay, almost all the government research institutes like ISRO, NL, BARC, okay, IPR, HL, BAIL, DRDO, Air Force, SAIL, etc., etc. These all institutes are using CFD for their research purpose. Okay, and if you look at the private organization, almost all the automobile organizations, okay, they are doing CFD at their level. Okay, and these are the different the ready-made, or say the code developed, available in the market. Okay, one which we have discussed is Fluent somewhere. Okay, which is a part of ANSYS. Now ANSYS is a company which has acquired Fluent. Okay, which is a solver. Apart from this, CFX is also solver. COMSOL Multiphysics is there, NSIT is there, ParaView is there, Pointwise is there. Even the Autodesk is having their own CFD tool now. Okay, so SolidWorks is also doing CFD now. So you see, almost all the modeling industries are now turning towards the CFD. So there is a large opportunity available in the market. If you want to learn CFD, you can make your career in this field. Okay, and CFD is a large in demand. Okay, so when I was there at the CSIR National Aerospace Laboratory during 2015 to 2017, okay, we worked on different softwares. Okay, and we were in close collaborative project with TU Munich of Germany. Okay, and HL, and then GTRE. So when we were doing project over there, okay, we have learned number of tools. Okay, so in Bangalore, if you go, it's a hub of CFD. Okay, there are a number of companies available. Okay, but apart from CFD, as I mentioned, that you should learn fundamentals of CFD, and some sort of problems are associated with CFD, like the convergence issue, consistency, stability criteria is required, conservativeness, okay, boundness, the transportiveness. So these are some of the additional, the problems which are still there in CFD. And if somebody who want to make their career in the field of CFD, after learning in depth, okay, they can go in the field and they can start working in the domain of turbulence modeling, which can resolve all these problems. Okay. So the question arises that how to improve CFD results, if these are the things, okay, and how we can improve the CFD results. So most of the CFD results which I have come across, or which I have seen, okay, how people are making those mistakes, are mainly based on the understanding of the problem, the associated knowledge, experience, and skill. Okay, so if we have not well understood the problem, okay, as people used to say that a well understood problem is half solved. Okay, so if you have understood the problem nicely, okay, it is like you have solved it half, right? So understanding the problem, okay, where the boundary conditions are required, how the model should be, how the meshing should be, okay, and then it is also a nice amalgam of knowledge, experience, and skills. So as and when you grow in this field, in this industry, you will learn, you will keep on learning on this type of problem. You can improve your results, right? And then the verification and validation is required. Okay, some sort of baseline validations are always available. So whenever you have, for example, you have an industry, okay, and you have a new problem that I want to uh, design a new pipe. As I gave you earlier example, I want to design a new pipe, and this pipe is having certain thickness. Okay, so as a CFD industry, what we used to do is we are first analyzing a simple baseline flow through that pipe, which they already have. Okay, so we are validating our results with the experimental results. Once these results are validated, then we are doing modification in the geometry. Okay, and that's how we are providing them the services. So this validation is also one of the most important tasks. So to become a CFD, successful CFD student, what I suggest is you should have some sort of CFD knowledge and numerical methods. Okay, we know that students are not focusing more on the mathematics part, but when we are in the field of engineering, okay, mathematics is one of the most important thing. Okay, so recently, I think last month I had delivered one lecture at Parole University. Okay, it was for the degree students. I have delivered entire talk on CFD, fundamentals of CFD, and there I had delivered an importance of mathematics in the field of CFD. Okay, so what are the mathematics involved? Okay, there are different things like when you have to switch, because we also do code development. Okay, code development is one of the initial tasks when we learn CFD. Okay, so when we do this type of things, we have to understand that some sort of like we are using Gauss divergence theorem. Okay, we are using matrices. Okay, inverse of the matrices. Okay, and then we are using different methods like pentadiagonal matrix algorithm. Okay, tridiagonal matrix algorithms. So these things are required. Okay, and the fluid, obviously, the fundamental knowledge of aerodynamics, fluid mechanics, heat transfer, solid mechanics. These are required skills. Okay, so if students who want to pursue their career in the field of CFD, they can be a code developer. Okay, so the code developer's job is to evolve new CFD software. For example, I gave you an example of turbulence modeling. Okay, so there's still a scope of opportunity, scope of improvement is there. Okay, so they can start working on a turbulence modeling. Okay, and then they can use this turbulence model to solve some CFD problem. Okay, so using this, they can be rewarded. Okay, so then the application engineer. So code developers are developing this numerical tools. Okay, and application engineers are applying those tools, and they are checking whether these tools are error free or not. Then there are testing engineers. So testing engineers are using those tools for a separate models or special purposes. Okay, so they are doing it for example, biomedical applications, or say for the internal aerodynamics or external flow analysis. Okay, for the combustion problem, for the multi-phase problem. Okay, so they are testing this solver for different problems. Okay, and that's how a global software is developed. Okay, and then one can be a technical writer or engineer, where their job is to extract the data. Okay, which is also which I also call as the data mining, which is a big problem, right? Because you can have a lot of data, but which data you need to analyze? Okay, which data you should consider? Okay, so that is called as the data mining. Okay, and then the post processing of those data. Okay, in terms of meaningful presentation is also required, because people are not interested in all the data; they are interested in a particular data. So if you are able to justify it, then you can penetrate in the CFD field. So what industry expects? Okay, for example, if we are into the business of consultancy, okay, so what I particularly expect from the mechanical background students are there. Okay, so I expect that at least students should have some sort of fundamental knowledge which you are already learning at your academic level. Okay, and then enhance your skill using the different tools. Okay, so when you are enhancing your skill using the different tools, then you should also have exposure of some exposure in terms of minor project or major project. Okay, so I always suggest that you learn different projects, you solve different projects, or you take those type of projects which are there, which are already being solved by some industry. Okay, and which can add some value to your resume. Okay, and these are some of the hot domains where a CFD engineer can enter. That is like turbo machines, multi-phase, combustion, IC engine, HVAC, heat and mass transfer, heat transfer, right? These are the popular job locations, okay, where student or CFD engineers are required at the most currently, right? So what we do at Apply Consultancy Services is we are into the service of complex CAD modeling, okay, for the machine part, automobile part, and aerospace parts. We are providing CFD services and also report services to mechanical, automobile, biomedical, HVAC, aerospace, and turbo machinery industries. Okay, we also do structural and thermal analysis for the mechanical, automobile, civil, and aerospace components. And we also supply industry training programs, okay, in the field of structural analysis, buckling analysis, CFD analysis with internal and external flow, thermal analysis, and turbo machinery analysis. And recently, we have launched our academia training and internship program, where we are guiding students. We are teaching them with different tools, and then the industry problems that we have solved. Okay, so that student can get interaction of the field of CFD along with the recent industry problem solutions. Okay, so these are the different industries to whom we have already served till now. Okay, directly or via our channel partners. So these are the different industries that we have supplied our services. And these are the MSME industries of Makarpura GIDC, Manjusa GIDC, Vagoria GIDC, Sachin GIDC of Surat, okay, where we have provided training programs. So this MSME industries wanted us to come and deliver our 1 week industry training on so and so particular tool. Okay, so we are providing kind of training to them for 1 week or 10 days as per their requirement. Okay, and based on the module which they want to learn. Okay, it is not so that all the people are required to know all the things. Okay, if the industry is willing to learn the buckling analysis, then we are solving buckling analysis problems with their tools only. Okay. And also we have delivered academia expert talks at Bhagwan Mahavir University, SVNIT Surat, KGIT, SVIT, Parul University in degree engineering, Silver Oak University, IEEE student chapter at Ahmedabad, and presently at the diploma engineering at Parul University. So these are the training and internship program at the Pi Consultancy Services. Okay, we are in the design of axial compressors, axial gas turbines, then the NSYS, CFD, and mechanical analysis in computer-aided modeling. So as a part of our industry program or internship program on the design and analysis of axial compressor, we are following this process where we are first analyzing the entire hand calculation based calculation for the required data, and then based on that we are making a geometrical model, okay, and then doing the mashing, okay, and then after we are analyzing it, then we are checking the performance map of the efficiency. So based on this is entirely a closed loop system. You can see here it's a completely closed loop system. If you are failing at one another, you need to go back and you need to recheck. Okay, so recently, I think just before a week or 5 days, we have completed our first batch of internship students. Those were 15. Those were 15 students from SVIT Vasad of the Department of Aeronautical Engineering, who have taken up this course of axial compressor design and analysis. Okay, so they all have designed a separate compressor rotor. Okay, and then they have analyzed the entire rotor performance. So that is how one can learn using the CFD tool. Then the axial turbine aerodynamic and design analysis. So this is the baseline design that we are doing at the first. Once we have calculated data, okay, we are segregating those data at different stations, and then we are analyzing it using the domain generation, okay, and then we are mashing it, and at the end we are analyzing it. So this is how we are doing the entire design and analysis of axial compressor and axial turbines. Okay. In the case of NSYS CFD, we are doing internal flow. We are teaching students as an internal flow, external flow, fluid structure interaction problems, where the structural load are taken inside the fluent, and then the fluid loads are also applied. So if the structure is failing, then they can analyze. For example, here one of the problem which we have solved is the engine fins. Okay, so engine inside temperature is there, so that thermal analysis is done first, and then the fluid analysis is done. Okay, so CFD is done, and this fin designs were optimized. Okay, so after we have extended this project recently, and we have designed different fin structures. Okay, so based on 3 different fin structures, we come up with one of the optimum fin structure design where the maximum heat dissipation can take place and that problem solution is delivered to the industry. Okay, so this is about the fluid structure interaction. Then the multi-phase problem can be solved where you have different phases. Okay, for example, you have boiling and nucleation kind of problem. Okay, or you have a pipe having air as well as water both. So that can be solved. Okay, a specific transport, which is also called as the combustion problem, can be solved. Okay, and the turbo machinery simulations. Apart from this, we are also providing internship in the field of ANSYS mechanical. So in the ANSYS mechanical, we are doing analysis like the structure analysis. You can see here, these are the components which were designed, which were modeled and then analyzed. Okay, and these are the two gears. Okay, so we had this problem of two gears. Okay, these are the spur gears, and it was analyzed that what is the maximum stress one can observe at which particular location. So that was done. So static structure analysis is involved, transient structure is involved, static thermal is there, transient thermal is there, buckling analysis is done. Okay, so these are the different ANSYS CFD and mechanical internship opportunities at Pi Consultancy. Apart from this, we are also providing services to industry as well as academia. Okay, we are also providing internship opportunities to students using CATIA and SolidWorks. Okay, so real life components are being modeled. Okay, because industry required to have this type of industry drawings. Okay, these are the design drawings. Okay, so we are doing this type of different CAD models. Okay, this is one of the internship program where student has entirely designed the gas turbine engine. Okay, so you can see here these are the low pressure compressor, then you have high pressure compressor, and then high pressure turbine, low pressure turbine, and then here is somewhere we are having combustion chamber. Okay, so this is entirely developed by a student, and this is the impeller problem that we have solved recently. And this geometry was modeled. So this is the geometry which I have taken from SolidWorks. So these are the different internship program at Pi Consultancy Services. So at the end, I just want to convey that if somebody want to draw their career in the field of CFD, okay, these are the most important things that one should take care. Generating geometry without any error. Okay, creating a fluid domain. Okay, that is also most important thing, as it should be as per the dimensions. Then the boundary condition definition, the material property if you are defining, okay, and then the convergence criteria. Okay, if you are not taking care about all these things, you will end up with the GIGO. So that is garbage in, garbage out. Okay, CFD is something that it will give you something. Okay, but whether that something is meaningful or not is purely on us. Okay, so how we are taking care of all these things, that is the most important thing. Okay, so I hope you enjoyed this this tour of computational fluid dynamics. It is no more colorful fluid dynamics. It is computational fluid dynamics, which involves the understanding of CFD fundamental, okay, and the knowledge of fundamental subjects like fluid mechanics, heat and mass transfer, okay, the structure analysis, structure mechanics, okay, and aerodynamics. So I thank you to the diploma mechanical engineering department at the Parul University for providing me this opportunity. Okay, this is one of the CFD analysis done using mask. You can see if you are not properly wearing your mask, okay, so water droplets or say the droplets can eject outside. But if you have properly fitted mask you have wear, then those droplets will be will not come out. Okay, it will remain there. So these are the type of analysis done by ANSYS software. Okay. So if you have any query, you can contact us on the pi.baroda@gmail.com or the given contact details. We'll be happy to help you. Thank you, sir. Thank you.
Thank you, sir. Thank you very much. And thanks to everyone. We appreciate you being here. Thank you very much, sir, again for sparing your valuable time. And thanks again to all for joining us for today's webinar. And we will see you on next time. Have a good day and thank you very much, sir. Once again. Thank you, sir.
Thank you, sir. Thank you.
Okay.